Hi everyone, this is Dr. T. Siva Nageswara Rao, working as Assistant Professor of Mathematics in the Department of Mathematics and Management Science. In this lecture, I am going to explain about Euler's theorem and Taylor's theorem, some solid examples on it. In previous lecture, I explained about Jacobian and functionally dependence. Before that lecture, I explained about limits, continuity, differentiability, that is partial differentiation of a function involving two variables. Now today I am going to explain Euler's theorem and Taylor's theorem. First one, Euler's theorem. Here see, Euler's theorem in this particular unit, we will talk about Euler's theorem for homogeneous function. So, Euler's theorem is applicable to homogeneous functions. When do you say a function f of x comma y is a homogeneous function? Condition is, we will replace in place of x with lambda x, in place of y with lambda y. Then the right hand side function is exists. That means if it is possible to take lambda power something as common from the whole expression, and the resultant expression is looks like f of x comma y, then only we can say f of x comma y is a homogeneous function of degree n. Now what is Euler's theorem? I already told, if you want to define Euler's theorem, the given function should be homogeneous function of degree n. Sometimes what will happen, assume that if I given a function is like this, u is equal to log of x square plus y square divided by x cube plus y cube. Assume. If I am substituting in place of lambda x with lambda x and y with lambda y, it is not possible to take out lambda power something as common from this expression. Then, in this case, we can say these first type of functions are not homogeneous. So, we will make it into homogeneous by taking x square plus y square is equal to x cube plus y cube, x square plus y square divided by x cube plus y cube is equal to e power u. I will take this e power u as z. So I will rewrite it as z of x comma y is equal to x square plus y square divided by x cube plus y cube. We will replace in place of x with lambda x and y with lambda y. So we will get finally z of lambda x comma lambda y is equal to lambda power minus 1 into z of x comma y you will get. So this is a homogeneous function of degree minus 1. If the given function is not homogeneous, we will convert it into homogeneous function by taking substitution. Right. Now what is Euler's theorem statement? If f of x comma y is a homogeneous function of degree n and has continuous first order partial derivatives, then x multiplied with dou f by dou x plus y multiplied with dou f by dou y is equal to n multiplied with f of x comma y. This is Euler's theorem for a function involving two variables. Similarly, we can extend for three variables also. For suppose, if I am taking f of x comma y comma z is a function involving three independent variables, then the Euler's theorem states that x multiplied with dou f by dou x plus y multiplied with dou f by dou y plus z multiplied with dou f by dou z is equal to n multiplied with f. This is how we can extend Euler's theorem for a function involving n number of variables. We'll see examples. Here our aim is to verify Euler's theorem. What is the given function? F of x comma y is equal to x square plus y square. Just by observing it, we can say very easily it is a homogeneous function of degree 2. Otherwise, we will checking homogeneity. We will replace in place of x with lambda x, in place of y with lambda y. So what you will get? Lambda x whole square plus lambda y whole square. Take out lambda square as common. That is lambda square multiplied by x square plus y square. So we will write this as lambda square multiplied by f of x comma y. So f of x comma y is a homogeneous function of degree what? 2. Why? The lambda power is 2. This is about n value. This is what we are taking n value as 2. Now, for verification, we need to show LHS is equal to RHS. What is LHS? X multiplied with dou f by dou x plus y multiplied with dou f by dou y. So we need to find first order partial derivatives 2f with respect to x comma y. So first we will calculate dou f by dou x value, that is 2x. Anyway, y is constant, its derivative is 0. Dou f by dou y, x is constant, y square derivative is 2y. Now we will substitute these values into here, that is x into 2x plus y into 2y. We will simplify. We will get 2x square plus 2y square. Take out 2 as common. Now what is the resulting expression? X square plus y square multiplied by 2. But what is x square plus y square? This is f of x comma y. So 2 multiplied by f of x comma y. Finally, what we got? X into fx. Fx means dou f by dou x. Y multiplied by fy is equal to 2 multiplied by f. It means what? We verified Euler's theorem statement. Next, one more example. Verify Euler's theorem for the function f of x comma y is equal to x cube plus 3x square y plus 3xy square and y cube. Similarly, first we will check for homogeneity. We will replace in place of x with lambda x, in place of y with lambda y. Now what is basically this expression? This expression is x plus y whole cube. So we will replace in place of x with lambda x and in place of y with lambda y. Then what you will get? Lambda x plus lambda y whole cube. Take out lambda as common. You will get lambda cube multiplied by x plus y whole cube. Then we will write it as lambda cube multiplied with f of x comma y. Therefore, this function f of x comma y is a homogeneous function of degree 3. Now, here our aim is to show x multiplied with fx plus y multiplied with fy is equal to n multiplied with f. Now consider LHS. Consider LHS. Here what are the requirements? Our aim is to find dou f by dou x and dou f by dou y. So, we will calculate dou f by dou x. Then, the derivative of x cube is 3x square. The derivative of 3x square y is 6xy. The derivative of 3xy square is 3y square. And the derivative of y cube is 0. Similarly, we will apply partial derivative to f with respect to y. So, x cube derivative becomes 0. And remaining expressions, the derivative of 3x square y with respect to y is the derivative of 3x square y with respect to y is 3x square. The derivative of 3xy square with respect to y is 6xy. The derivative of y cube is 3y square. So these are the first order partial derivatives. We will substitute it into the respective places. Later multiply with x comma y and take the constants as common from the expression. You will get this. We can write this as 3 multiplied with f of x comma y. So what we proved? X multiplied with fx plus y multiplied with fy is equal to 3 multiplied with f. So this is the verification of Euler's theorem. If you want to evaluate the value of x multiplied with fx plus y multiplied with fy by using Euler's theorem, just identify what is the degree of homogeneous function and substitute in place of n with that respective value. You will get the value of x multiplied with fx plus y multiplied with fy value. So these are the worksheet problems. Please practice all these problems. Next, we will see about Taylor's theorem for two variables. Now here, anyway, we are taking two variables. So my function involving two variables, x and y. Let f of x comma y be a function having continuous partial derivatives up to second degree, up to second order or higher order at a point a comma b. Then the Taylor series expansion of f of x comma y about a point a comma b is given by f of x comma y is equal to f of a comma b plus x minus a multiplied with fx of a comma b plus y minus b multiplied with fy of a comma b plus 1 by 2 factorial into x minus a whole square fxx of a comma b plus 2 into x minus a into y minus b multiplied by fxy of a comma b plus y minus b whole square into fyy of a comma b plus 1 by 3 factorial into x minus a whole cube multiplied by fxx of a comma b plus 3 multiplied by x minus a whole square into y minus b into fxxy of a comma b plus 3 into x minus a into y minus b whole square fxyy of a comma b plus y minus b whole cube into fyy of a comma b square bracket plus and so on. So this is the Taylor series expansion of the given function involving two independent variables x comma y. Here what is the notation for fx? Dou f by dou x. Fy? Dou f by dou y, first order. Here fxx, fxy, fyy, second order partial derivatives. Now coming to here, third order partial derivatives and so on. Now if you want to write the Taylor's theorem for a function involving x comma y about a point origin, we will replace in place of a with 0 and b with 0. If you substitute a with 0 and b with 0 in this expansion, then you will get, this is the formula. For this we have a special name called Maclaurin series of the given function f of x comma y about the origin. Now we will see examples, solid examples. Find the third degree Taylor's expansion of the given function f of x comma y is equal to e power xy about a point 0 comma 0. Now what is the given function f of x comma y? E power x plus y. What is the given point? 0 comma 0. So we are going to find Maclaurin's expansion. Of course, every Maclaurin's expansion is a Taylor's expansion. Taylor's expansion of the given function about a point 0 comma 0. So this is the formula. Here our aim is to find what are the values of fx, fy, fxx, fxy, fyy, fxx, x, fxxy, fxyy, fyyyy. After finding first order partial derivatives, second order partial derivatives and third order partial derivatives, we will substitute in place of x comma y with 0 comma 0. Here is the given function. First, we will find partial derivative with respect to x. Anyway, the derivative of exponential function is always exponential function. So, the derivative of f of x comma y with respect to x is fx. Its value is e power xy. We will substitute in place of x with 0 and y with 0. That is again 0 plus 0. You will get 1. So, fx value is 1. Similarly, fy value is also 1. Again, calculate all possible second order partial derivatives in the same manner and substitute in place of x with 0 and y with 0. You will have second order partial derivatives. After finding all possible second order partial derivatives, substitute in place of x with 0 and y with 0. Here all second order partial derivatives values is equal to 1. In the same way, all possible third order partial derivatives also you will get 1. Substitute these values into this formula. You will get f of x comma y is equal to this expansion. Now simplify these terms, you will get the final answer is this one. So this is how we will express the given function e power x plus y as like a series terms like powers of xy, maybe product terms. Now second example, this is the given function. Here our aim is to find Taylor series expansion. If you are observing this, here we are not the given question does not contains any name like Taylor's or Maclaurin's. Here what is the given point 1 comma 2 means this is other than origin. So obviously here we will calculate Taylor's expansion of f of x comma y about the given point. This is what you need to understand. So this is the Taylor's expansion of the given function up to second order. Anyway, in the given question we need to take only second degree. So we will take up to second order derivatives. Now here first one f of 1 comma 2. That means in place of x we will substitute 1. In place of y we will substitute 2. You will get answer as 7. Next we will find first order partial derivatives. Means apply partial derivative to f of x comma y with respect to x as well as with respect to y. You will get f of x as 2x plus y and fy as x plus 2y. Now substitute in place of x with 1 and y with 2 in first order partial derivatives. You will get answers as 2 comma 1 respectively. Now substitute all these values that is in place of x with 1 and y with 2, you will get fx value as 4 and fy value as 5. Now coming to second order partial derivatives, we will find fxx. So you will get fxx value as 2, fyy value as 1, fxy value as 1 and fyy value as 2. Now substitute all these partial derivative values into Taylor's expansion of the given function f of x comma y. You will get the final answer is in this form. So this is how we can find the Taylor series expansion of the given function involving two variables x and y. Now these are the worksheet problems. Using Taylor's theorem, expand the following functions about the given point. Few problems are given about the point origin, means the Taylor series the Taylor's expansion is same as Maclaurin's expansion. Other than the origin, I given one problem, means two problems. One is 1 comma 1 and other one is 1 comma 0. Please try to solve all these problems. So till now I explained Euler's theorem. If you want to apply Euler's theorem, the given function should be homogeneous function of degree n. How will verify homogeneity? You need to replace in place of x with lambda x and in place of y with lambda y. So f of lambda x comma lambda y is equal to lambda power n multiplied by f of x comma y. Then only we can say f of x comma y is a homogeneous function of degree n. Later, we will verify Euler's theorem. If a function involving two independent variables x comma y, then the statement is x multiplied by dou f by dou x plus y multiplied with dou f by dou y is equal to n multiplied with f, where f is f of x comma y, function involving two independent variables. That is verification part. Similarly, I started with Taylor's theorem, that is Taylor's expansion of the given function f of x comma y. This expansion involving first order partial derivatives, second order partial derivatives, third order partial derivatives, and so on. In view of Taylor's expansion of the given function about a point, what type of point it is? Either it is origin or other than the origin. If it is origin, the Taylor's theorem is also called Maclaurin's theorem. Otherwise, it is always Taylor's theorem only. Thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.